Various alloys that can be deformed superplastically are given here. Titanium alloys can be superplastically deformed. M value and percentage elongation obtained and temperature range, everything is given here in this table. It has wide applications in aircraft industries. These are the various alloys which has application in aerospace industries. Airframe can be manufactured. Aircraft engines applications are concerned. As far as applications are concerned, airframes, aircraft engines, compressor parts, cases, structural parts, disc for aircraft turbine, compressor, aircraft seat components, aircraft hydraulic components can be manufactured using these titanium alloys. Mechanical properties. This plot is made between stress versus temperature for three different grain size, namely fine grain size, normal grain size, coarse grain size. For fine grain size, there is a drastic change in the stress as the temperature increases. In the case of normal grain size, also normal grain size, the stress decreases with increasing temperature. In the case of coarse grain size, decreases with increasing temperature like this. So fine grain material is suitable for this temperature, for this particular temperature range, fine grain materials are suitable. This is the mechanical properties. This plot is made between M and log sigma dot. Sigma dot is the strain rate. Epsilon dot is strain rate. This is the region 1, this is the region 2A, this is region 2B, this is region 3. Region 1, M value is very low, so no superplasticity will take place. In 2A, superplasticity will take place. Maximum superplasticity will be taking place in this region. In this region, 2B, the superplasticity is being slowly lost. In the region 3, there is no superplastic deformation. Necessary condition for superplastic forming is given here. Duplex structure, multiphase structure is suitable for superplastic deformation. Types of phases and the distribution is very important. Grain boundary condition is important. Temperature, strain rate, and grain size are also important. These factors influence the degree of superplasticity. Lower retractive temperature, better is the superplastic properties. Ternary retractives are more superplastic than binary retractives. Strain rate should match with the velocity of the diffusion process. This improves the superplasticity. Coarse grain structure dissolved second phase particles eliminate the strain rate sensitivity and high elongation. Non-deformable second phase particle found in the dispersion hardening alloys also eliminates fine grain size and leads to cavitation. Undissolved carbides also prevent superplasticity. For example, iron carbide prevents superplasticity. Production of ultra-fine grain size. Cold work or hot work commercially pure metal to produce fine grain size, stabilize the grain size by dispersion of impure particles which spin the grain boundaries predominantly. Grain boundaries must be pinned down predominantly. We know that capital R equal to 4 into small r divided by 3f, where r is the radius of the grain, small r is the radius of second phase particle, f is the volume fraction of the second phase particle. As the volume fraction should be, as far as possible, radius of the second phase particle should be globular and should be small as far as possible. From the above relation, the minimum grain size can be obtained depends on small r and more f. When second phase particles are present, the grain boundary is eliminated. Grain boundary is eliminated. This leads to decrease in grain boundary energy. When the decrease in grain boundary energy is more, the system results in grain growth. For example, zirconium addition in aluminum alloys will be helpful. Production of ultrafine gases. Cast alloy eutectic eutectide polyphase is suitable for superplastic deformation. Work them by about 60 to 70% to get an intimate mixture of phases. Stable ultrafine grains less than 10 micrometer is suitable for superplastic deformation. It can be obtained with help of particles relatively coarse and well separated. This is essentially exploited, for example, zinc, aluminum, copper. Powder metal is several advantages. Segregation and bonding makes unsuitable in conventional method. Compact alloy, hot extruded, grain repellent can be obtained. Spinodal decomposition is suitable. Strain rate. Strain rate. Uniform strain and creep rate d epsilon by dt increases with the decrease in grain size. The epsilon dot is proportional to 1 over L by B, where L is the grain size, B is a constant which varies from 2 to 3. Ultrafine grain size, increase in strain rate is equivalent to increase in grain size, which has a deleterious effect, the bad effect on superplasticity. Strain rate increases exponentially with the temperature. Fine grained exhibit greater recovery. For example, sigma equal to sigma I, alpha plus epsilon. Sigma I stress at zero strain per given strain rate. Alpha slowly varies with strain rate. Superplastic deformation is essentially strain independent, and structural changes are absent. M increases with the decreasing grain size. M increases with the increasing temperature. Maximum M value is reached at the temperature just below the phase boundary, defining this upper limit of the two-phase field. Temperature difference of M is more in the region second compared to region 1 or third. M is independent of strain rate and dependent on temperature. Example, zinc aluminum eutectide alloy. Reference book is K. Padmanabhan and Davis, Superplasticity. And